Subscribe to the channel so you don't miss out on any of these videos. Imagine a distant galaxy billions of light years away from Earth. In that remote part of the universe, something incredible happens. A single, powerful burst of radio energy erupts, brighter than anything else around it for just a fraction of a second, and then it's gone. This split-second event, mysterious and intense, is known as a fast radio burst, or FRB, and it's one of the most baffling phenomena astronomers have encountered in recent decades. These signals, lasting only a few milliseconds, have left scientists puzzled since their discovery in 2007. Their origin, their nature, and their purpose remain largely unknown, making FRBs a powerful source of intrigue and speculation in the world of astrophysics. As scientists continue to grapple with this enigma, the questions only multiply. Where do these signals come from? Are they caused by natural cosmic events or by something else entirely? Could they even be intentional messages from an intelligent civilization? In this exploration, we dive into the deep mystery of fast radio bursts, their potential causes, recent discoveries, and the significance of their study in our understanding of the cosmos. The story of fast radio bursts begins in 2007, when the first FRB was identified by a team of astronomers led by Duncan Lorimer and his student, David Narkevic, at West Virginia University. This burst was buried in archival data from the Parkes Radio Telescope in Australia, which had originally recorded the signal in 2001. The discovery was completely unexpected. The signal was brief, extraordinarily powerful, and seemed to come from billions of light years away, outside of our Milky Way galaxy. The signal's brevity and intensity stunned astronomers, prompting them to question what kind of phenomenon could create such a burst. This initial FRB, now called the Lorimer burst, sparked a wave of interest and an enduring quest to understand what was happening in the depths of space. One of the defining characteristics of FRBs is their sheer intensity. Each burst can release more energy in a few milliseconds than our Sun does in several days. These bursts also appear to travel great distances, crossing billions of light years before reaching Earth, which suggests they originate in extremely powerful environments. Adding to the mystery is the fact that FRBs are scattered and spread out over different parts of the sky, with no apparent pattern in their location or timing. Some FRBs have only been observed once, while others have been detected multiple times from the same source, known as repeating FRBs. This dichotomy between one-time and repeating FRBs has raised more questions about the mechanisms behind them and the cosmic conditions necessary to produce such brief yet intense radio emissions. A major breakthrough in the study of FRBs came in 2012, with the detection of the first repeating FRB, known as FRB 121102. This discovery was monumental, as it provided a significant clue that not all FRBs were single, isolated events. FRB 121102 was found to be originating from a distant dwarf galaxy about 3 billion light-years from Earth, suggesting that some FRBs could be linked to specific locations and potentially specific types of astrophysical objects. This repeating signal opened new doors for astronomers, who began to speculate about the types of cosmic entities that could generate such emissions repeatedly. Among the leading theories is that FRBs might be produced by young, highly magnetized neutron stars, known as magnetars, which are known for their extreme energy emissions. Magnetars are rare and volatile, with magnetic fields billions of times stronger than that of Earth, capable of producing intense bursts of radio waves and other types of radiation. However, while magnetars are a promising candidate, they are not the only possibility, and some researchers remain skeptical about whether magnetars alone could explain all observed FRBs, especially given the diversity of their properties. FRBs have proven to be invaluable in studying the vast, intergalactic spaces through which they travel. As these radio waves journey across billions of light years, they pass through the interstellar and intergalactic media, regions filled with particles, magnetic fields, and plasma that interact with the radio signals in unique ways. Scientists can analyze these interactions to gather information about the matter that FRBs pass through, effectively using these bursts as cosmic probes. This has allowed astronomers to gain insights into the large-scale structure of the universe, including the distribution of gas and magnetic fields between galaxies. This approach has even contributed to addressing a long-standing puzzle in astrophysics: the missing baryon problem. Baryons, a type of subatomic particle that includes protons and neutrons, are expected to make up a significant portion of the universe's ordinary matter. Yet, for years, a large portion of this baryonic matter eluded detection. However, FRBs have helped astronomers locate these missing baryons as the bursts interact with this matter on their way to Earth, revealing the otherwise invisible baryons in the cosmos. Despite the progress made in recent years, the cause of FRBs remains one of the most intriguing puzzles in astrophysics. Scientists have proposed a wide range of possible explanations, from the mundane to the extraordinary. One of the more mainstream hypotheses is that FRBs may be associated with catastrophic events, such as the collision of neutron stars or the collapse of massive stars into black holes. Such events would release enormous amounts of energy in a short period, which could explain the intense bursts of radio waves. Another theory suggests that FRBs could result from highly energetic processes in the vicinity of black holes or within the extreme magnetic environments around neutron stars. Yet, there are other theories, more speculative in nature, that propose FRBs might be generated by advanced alien civilizations using high-powered radio signals as a form of communication or propulsion. Though the idea of alien technology causing FRBs is still largely speculative, it captures the imagination and underscores the mystery that surrounds these bursts. In recent years, the pace of FRB discoveries has accelerated, thanks to advances in radio astronomy technology and the development of new observational tools. The Canadian Hydrogen Intensity Mapping Experiment, CHIME, a powerful radio telescope located in British Columbia, has become a leader in the hunt for FRBs. CHIME is capable of observing large portions of the sky simultaneously, allowing it to detect FRBs more frequently than previous instruments. Since coming online, CHIME has detected hundreds of FRBs, including many repeaters, greatly expanding the known sample of these events and providing invaluable data for analysis. The discoveries made by CHIME and other observatories have demonstrated that FRBs are more common than once thought, suggesting that thousands of these bursts may occur every day across the universe. This abundance of data is critical in helping scientists identify patterns, compare different types of FRBs, and refine their theories about what could be causing these mysterious radio signals. One of the most intriguing findings about FRBs is the diversity in their properties. Some bursts show complex structures, with multiple peaks in their emission, while others are single, sharp spikes. Additionally, while some FRBs repeat, others do not, and the intervals between repetitions vary widely. This diversity has led scientists to speculate that FRBs might not have a single origin. Instead, they could be produced by multiple types of astrophysical processes, with different types of FRBs corresponding to different causes. For example, some researchers propose that one-time FRBs might be linked to catastrophic events, like supernovae or mergers of neutron stars, while repeating FRBs could be caused by phenomena associated with active, long-lived sources, like magnet-ars or young pulsars. This diversity adds another layer of complexity to the mystery, as each new discovery raises more questions about how these bursts are generated and what conditions are necessary for their production. Another key aspect of FRB research is the role that these bursts could play in helping us understand the distribution of dark matter in the universe. While dark matter does not interact with electromagnetic radiation directly, it does exert gravitational influence on regular matter. By studying the dispersion and distribution of FRBs across the universe, scientists can gain insights into the presence and distribution of dark matter, as the gravitational influence of dark matter may affect the pathways that these radio waves take on their journey to Earth. This aspect of FRB research is still in its early stages, but it offers an exciting potential for using FRBs as a tool for probing the elusive properties of dark matter, which remains one of the greatest unsolved mysteries in cosmology. The discovery of FRBs has also led to the development of innovative techniques for locating and studying these events. One of the biggest challenges in FRB research is that these bursts are incredibly brief and can appear at random locations in the sky, making it difficult to pinpoint their exact sources. However, recent advancements in fast imaging techniques and improved data processing capabilities have enabled astronomers to locate some FRBs with much greater precision. In 2020, astronomers using the CHIME telescope and other observatories managed to trace an FRB to a specific region within our own galaxy for the first time. This FRB, known as FRB 200428, was found to be associated with a known magnetar in the Milky Way, providing direct evidence that at least some FRBs can originate from magnetars. This breakthrough was a major step forward in FRB research, supporting the magnetar hypothesis and offering a tantalizing glimpse into the mechanisms that might be at play in these enigmatic bursts. However, despite these advances, FRBs remain a profound mystery. Each new discovery adds to our understanding but also raises new questions that deepen the enigma surrounding these bursts. Scientists are still working to determine the range of astrophysical processes that could produce such powerful, short-lived radio signals, and they continue to search for patterns that might reveal more about the origins of FRBs. Some researchers are hopeful that with continued advancements in radio astronomy, we may eventually be able to determine whether FRBs are produced by a single mechanism or by a variety of sources scattered across the cosmos. As they pursue answers, astronomers are expanding our knowledge of the universe in ways that could have implications for our understanding of cosmic phenomena far beyond FRBs themselves. Each FRB detected and analyzed offers a small piece of a vast cosmic puzzle, one that has the potential to transform our understanding of the universe's structure, behavior, and perhaps even its history. This quest for answers, driven by a combination of curiosity, advanced technology, and the relentless mystery of the unknown, lies at the heart of the human drive to explore and understand the cosmos. One of the biggest challenges in studying FRBs has been their random and transient nature. Unlike pulsars, which emit regular, predictable signals, or even black holes, which have relatively stable emission patterns, FRBs flash once and are gone, or, in the case of repeaters, return on unpredictable timescales. This irregularity complicates efforts to study them, as scientists must rely on continuous monitoring and increasingly sensitive telescopes to catch these fleeting signals. Even with powerful instruments like CHIME, which surveys large swaths of the sky at once, the unpredictable timing of FRBs remains a challenge, making each detection a rare and valuable opportunity to gather data. Adding to the complexity, there are still significant gaps in our understanding of the environments in which FRBs occur. While the discovery of repeating FRBs has pointed to potential origins in young, magnetically intense regions of dwarf galaxies, not all FRBs conform to this pattern. Some FRBs have been traced back to galaxies similar in size and structure to the Milky Way, suggesting that a wide range of environments might be capable of producing these bursts. This variability hints that FRBs might not only originate from different types of galaxies, but could also be associated with diverse astrophysical phenomena. These differences in origin could lead to different types of FRBs, each with unique characteristics based on the specific environments and objects that create them. Beyond the astrophysical implications, FRBs have also sparked curiosity about the possibility of extraterrestrial intelligence. The brief, intense nature of FRBs initially led some scientists and enthusiasts to speculate whether these signals might be intentional broadcasts from advanced civilizations. The theory gained traction due to the sheer strength of FRBs, which suggested that if they were artificial, they would require a highly advanced technology to generate such powerful bursts. While the extraterrestrial hypothesis remains on the fringes of scientific consensus, it has fueled interest in FRBs among scientists and the public alike. Researchers studying the potential for extraterrestrial origins focus on analyzing the patterns within FRBs to see if there's any sign of artificial structure, such as a repeating sequence, that could indicate intentional communication. So far, no definitive evidence has been found to support this idea, but the hypothesis continues to be explored, reminding us of the vast unknowns that still exist in the universe. Another theory that has attracted attention is the idea that FRBs could be related to cosmic strings, hypothetical one-dimensional defects in spacetime that may have formed in the early universe. According to some theoretical physicists, these cosmic strings might create bursts of energy when they interact or experience tension. If such strings were to oscillate or snap, they could theoretically produce intense emissions of energy, potentially explaining the intense, short-lived nature of FRBs. While this idea is highly speculative, it reflects the wide range of theories scientists are willing to consider in their quest to understand FRBs. Cosmic strings are a concept rooted in fundamental physics and the early moments of the universe, and their possible connection to FRBs introduces fascinating questions about the origins and evolution of the cosmos. In the midst of all these theories, one fundamental question remains: why do some FRBs repeat, while others do not? This difference has led scientists to classify FRBs into two broad categories: one-time events and repeaters. Repeaters like FRB 121102 emit bursts from the same location over time, while others appear only once and never return. Some scientists suggest that the repeating FRBs may come from neutron stars or magnetars in unique environments that allow for repeated emissions. The non-repeating FRBs, on the other hand, could be tied to cataclysmic events, such as the collision of neutron stars or the birth of black holes, that produce a single, intense burst of radio waves before fading away forever. The presence of both types of FRBs suggests a fascinating diversity in their origins and hints that multiple mechanisms might be responsible for creating these bursts. However, the true reasons for these differences remain elusive, adding another layer of mystery to the already enigmatic world of FRBs. As technology advances, the hope is that future telescopes will provide even greater insights into the nature of FRBs. New facilities like the Square Kilometre Array, SKA, an enormous radio telescope currently under construction in South Africa and Australia, are expected to be capable of detecting FRBs at unprecedented sensitivity and detail. With an array of antennas spread over vast distances, the SKA will allow astronomers to pinpoint the locations of FRBs with remarkable precision, potentially providing answers to questions about their origins and mechanisms. Additionally, as more observatories around the world coordinate to monitor FRBs, scientists may be able to establish patterns or trends that will shed light on the conditions needed to produce these bursts. The SKA's capabilities are anticipated to revolutionize radio astronomy, potentially leading to a clearer understanding of FRBs and their place in the universe. The study of FRBs is not only about solving an astrophysical puzzle, it also has profound implications for our broader understanding of the universe. These bursts, traveling across billions of light years, carry within them information about the cosmos that is often inaccessible by other means. By examining the way FRBs interact with the matter they encounter, astronomers can gain insights into the conditions and composition of intergalactic space. This knowledge, in turn, contributes to our understanding of cosmic phenomena like galaxy formation, dark matter distribution, and the structure of the universe on a grand scale. In this way, FRBs serve as a kind of cosmic lighthouse, illuminating the vast and often hidden components of the universe. Perhaps one of the most compelling aspects of FRBs is the sheer sense of wonder they inspire. The fact that we are detecting these bursts, sent across billions of light years from mysterious sources, reminds us of the vast scale of the universe and the limits of our current understanding. FRBs are a reminder of how much there is yet to discover about the cosmos, from the behavior of extreme environments to the fundamental nature of reality itself. The ongoing quest to understand FRBs is a testament to the curiosity and resilience of the scientific endeavor, a willingness to embrace the unknown and to push the boundaries of human knowledge in the search for answers. In the coming years, as telescopes like CHIME, SKA, and others continue to scan the skies, the likelihood of detecting more FRBs will only increase. Each new detection will bring new data and potentially new revelations about the forces that shape our universe. With each discovery, scientists will be one step closer to understanding whether FRBs are the product of isolated events, recurring processes, or perhaps something even stranger. The study of FRBs is a vivid reminder of the vast unknowns that still lie beyond our reach, waiting to be uncovered by future generations of scientists. As we consider the possibilities, the questions surrounding FRBs also serve as a reminder of the limits of our current technology and understanding. Despite remarkable advancements, we are only beginning to scratch the surface of what FRBs might reveal about the universe. Each new discovery offers a tantalizing glimpse into the complexities of the cosmos, hinting at answers to questions we may not even know to ask yet. The mystery of FRBs is not just a scientific puzzle, it is a journey into the unknown, a chance to explore phenomena that lie at the edge of human knowledge and imagination. In a universe filled with mysteries, from black holes to dark matter to the origins of life itself, FRBs stand out as a particularly compelling enigma. They are a reminder that for all our scientific achievements, the universe still holds many secrets, hidden within its vastness and complexity. And while the answers may remain elusive, the search for understanding continues, driven by the innate human desire to comprehend the cosmos and our place within it. The mystery of FRBs is one that speaks to humanity's innate drive to uncover the unknown. FRBs aren't just another puzzle for scientists to solve, they are glimpses into a realm of extreme physical processes, possibly offering insights that reach into the very nature of space-time and the building blocks of the cosmos. Each FRB, with its ephemeral signal traveling vast intergalactic distances, brings with it knowledge that's largely hidden within the burst's properties. By studying the shape, duration, polarization, and dispersion of these signals, researchers tried to peel back layers of information about the regions through which these bursts traveled, potentially unlocking secrets of intergalactic space and the large-scale structure of the universe. One significant aspect of FRBs is the high dispersion measure, which has intrigued scientists. Dispersion measure refers to the delay of radio waves as they travel through space, caused by interaction with electrons in the interstellar and intergalactic medium. The dispersion measure provides an estimate of the amount of matter the FRB has passed through, effectively offering a rough gauge of the distance to its source. FRBs tend to have extremely high dispersion measures, implying they originate far beyond our galaxy. The further away the source of the burst, the more interactions it has with particles in space, delaying the signal. This high dispersion points to origins in other galaxies, likely billions of light years away, and hints at how much there is to learn about intergalactic space, especially the mysterious missing baryonic matter, thought to make up a significant part of the universe's mass. Interestingly, FRBs could also serve as cosmic probes that help scientists map this elusive intergalactic matter. Observing multiple FRBs from different regions in the sky may allow researchers to construct a sort of cosmic survey, using FRBs as tracers of the matter between galaxies. This prospect excites astrophysicists because such a map would contribute to solving long-standing mysteries about the large-scale structure of the universe, providing new insights into the distribution of matter. The potential of FRBs to illuminate the elusive nature of intergalactic space means they are not only a cosmic mystery, but also an invaluable tool in the search for hidden aspects of the universe. The study of FRBs has also led to advances in the development of new technologies and data analysis techniques. Detecting and processing FRBs requires sophisticated algorithms to sift through enormous amounts of data collected by telescopes. For instance, CHIME and other radio telescopes gather massive datasets in real time, requiring machine learning and advanced signal processing techniques to identify FRBs amid a sea of cosmic noise. The sheer data volume pushes the limits of current computational power, spurring innovations in hardware and software that are increasingly essential in modern astronomy. These technological advances, driven by the search for FRBs, are likely to have applications in other scientific fields and may lead to improvements in areas ranging from telecommunications to data analytics. Moreover, as data from FRBs accumulates, it contributes to the development of more refined models in astrophysics. With more detections, scientists can begin to categorize FRBs, analyze their frequency, and identify any potential correlations with other astrophysical phenomena. Each new piece of data adds to a growing repository of information that future scientists will use to test theories, uncover patterns, and ultimately seek answers about what mechanisms could produce such powerful signals. By building a foundation of knowledge, today's researchers are laying the groundwork for the breakthroughs of tomorrow. One particularly exciting recent development has been the discovery of FRBs that appear to exhibit periodic behavior. While most FRBs seem random, a few show signs of periodicity, meaning that they recur at regular intervals. For instance, FRB 180916.J0158+65, discovered by CHIME, was observed to repeat on a 16-day cycle. This finding was unexpected, as it suggested a predictable underlying mechanism, possibly involving binary star systems or other periodic astronomical phenomena. This periodicity provides a potential key to understanding certain types of FRBs, as it points to a stable, regular process that produces the bursts, distinct from the randomness seen in other FRBs. If this periodicity can be observed in more FRBs, it may reveal patterns that indicate what types of celestial objects are responsible for producing them. Another area of study is polarization, or the orientation of the FRB's electromagnetic waves. By examining the polarization of FRBs, scientists can infer details about the magnetic fields that the radio waves pass through on their journey to Earth. FRBs with high polarization may suggest origin points in extreme magnetic environments, like those surrounding magnetars. The discovery of FRB 121102, a repeating FRB with a high degree of polarization, hinted at such an environment, leading scientists to suspect it originated near a powerful magnetic field or within a young, highly magnetized region. The presence of polarized signals thus offers clues to the environments surrounding FRBs, providing valuable hints about their possible sources. The role of magnetars in generating FRBs has gained attention in recent years. Magnetars are a type of neutron star with extremely powerful magnetic fields, and they are known to emit bursts of X-rays and gamma rays. Given the extreme conditions of these stars, scientists theorize that magnetars might occasionally emit bursts of radio waves as well, potentially explaining at least some FRBs. In 2020, astronomers observed an FRB-like signal from a magnetar within our own galaxy, named SGR 1935+2154. Although weaker than the extragalactic FRBs typically detected, this burst resembled them closely enough to suggest that magnetars could indeed be one source of FRBs. This discovery marked the first time an FRB-like signal had been observed within our galaxy, lending significant weight to the magnetar hypothesis and giving researchers a valuable local example to study. However, not all scientists are convinced that magnetars are the sole explanation for FRBs, especially given the differences observed between repeating and non-repeating FRBs. Some researchers believe that while magnetars could account for certain FRBs, others may arise from completely different phenomena. This idea has led to what's known as the two-source hypothesis, which proposes that there may be multiple astrophysical processes capable of generating FRBs. The idea of multiple sources fits well with the diversity observed among FRBs, including differences in duration, polarization, and repetition. If the two-source hypothesis proves correct, it would mean that FRBs are not a single phenomenon but rather a collection of different types of bursts with different origins, each adding to the mystery and complexity of the field. The possibility that FRBs could come from a variety of sources has profound implications for astrophysics. Each type of source would contribute uniquely to our understanding of the universe, as studying different FRB sources could reveal new insights into the extreme conditions of their origin environments. From magnetars to neutron star collisions, each potential source represents an opportunity to learn more about the limits of known physics, shedding light on aspects of high-energy astrophysics that are still poorly understood. This diversity of sources could also explain why FRBs show such a wide range of properties, as each origin scenario would produce bursts with distinctive characteristics. In addition to the quest to understand FRBs themselves, there is also interest in their potential to shed light on broader cosmic mysteries. For example, FRBs may provide indirect evidence for dark matter. Some scientists have suggested that FRBs could interact with dark matter as they travel across the universe, with subtle distortions in the FRB signal possibly revealing clues about dark matter's properties and distribution. While this idea is still highly speculative, it highlights the potential of FRBs as a tool for probing the unknowns of astrophysics. If FRBs can indeed be used to study dark matter, they could open a new window into understanding this enigmatic component of the universe. Another exciting application of FRBs is in the study of gravitational waves. If an FRB were detected in conjunction with a gravitational wave event, such as the collision of two neutron stars, it could provide a wealth of information about the physics involved. Simultaneous detections would allow scientists to cross-reference data from the FRB with the gravitational wave signal, offering insights into the energy and dynamics of the event. This type of multi-messenger astronomy, combining different kinds of observations, is a powerful approach that has already yielded new insights in the study of black hole mergers. If FRBs could be observed in tandem with gravitational wave events, they might reveal information that could not be obtained from either signal alone. Despite all these potential avenues of discovery, FRBs remain, in many ways, an unsolved mystery. Their fleeting nature, combined with the immense distances they travel, poses a formidable challenge to researchers. Yet, each new observation brings us closer to understanding what these bursts signify. FRBs are like postcards from the far reaches of the universe, each one carrying a cryptic message from an era and place that are far removed from our own. They remind us that, despite the incredible progress of modern science, there is still much about the cosmos that we have yet to comprehend. The mystery of FRBs, much like other great enigmas in space, inspires not only the scientific community but also the public imagination. The vast, unexplored regions of space hold a near-mythical allure, and FRBs have become emblematic of the strange, unpredictable nature of the universe. They are an invitation to wonder and speculate, to imagine what other secrets might lie hidden among the stars. As technology advances and more FRBs are detected, the hope is that these enigmatic signals will eventually yield their secrets. Each burst, whether it repeats or occurs just once, adds a little more to our understanding. And while we are still in the early stages of studying FRBs, the scientific curiosity they inspire is bound to lead to exciting discoveries in the years to come. The mystery of fast radio bursts stands as a testament to the boundless curiosity that drives humanity forward, a reminder that every answer opens up new questions and that the universe, in all its vastness, will continue to surprise and inspire those who seek to understand it. The enigmatic nature of FRBs highlights just how little we truly know about the forces and objects at work in the universe. They are but one of many cosmic mysteries, yet they stand out because they represent a combination of extreme physics and great distances that challenge our current understanding. Even the very act of detecting an FRB is, in some ways, a triumph of technology and science, showing how much we've advanced yet how far we still have to go. Each FRB detection is like a breadcrumb left behind, pointing scientists toward the immense and largely unexplored space between galaxies. These signals have likely traveled for billions of years, passing through gas, magnetic fields, and possibly dark matter, to finally reach our detectors. Imagine a single radio pulse crossing light years of space, skimming by distant stars, interacting with clouds of gas and dust, maybe even warping slightly under the influence of gravitational fields from unseen objects. By the time it reaches Earth, the original signal is stretched and altered by its journey, carrying within it a wealth of information about the cosmos. Understanding the physical origins of FRBs could, therefore, provide insights into many other cosmic phenomena. Researchers often draw comparisons to pulsars, another type of radio-emitting object discovered in the 20th century. When pulsars were first detected, they were equally mysterious. At first, their precise, repeating signals led some scientists to think they might be signals from extraterrestrial intelligence, an idea famously dubbed LGM, or Little Green Men. Eventually, scientists discovered that pulsars were rapidly spinning neutron stars emitting beams of radio waves, and this revelation has since transformed our understanding of extreme physics. FRBs may have a similarly transformative potential, though they are vastly more powerful and less regular than pulsars. If scientists can determine what powers these intense radio bursts, it could reveal entirely new astrophysical mechanisms that are yet to be theorized. One of the most exciting aspects of FRB research is that it is still very much in its infancy. Each new observation brings with it the possibility of fundamentally shifting our understanding of these phenomena. For instance, the differences between repeating and one-time FRBs suggest that we might be observing not one type of event, but multiple classes of cosmic phenomena that all produce similar radio bursts. This variability could indicate that FRBs might be produced by several different types of objects or events, from the collapse of massive stars to the collision of compact objects like neutron stars. The idea of repeating FRBs has led scientists to consider that at least some of these signals might come from extremely powerful, active galaxies or cosmic environments. One possible origin is that of highly magnetized neutron stars, known as magnetars, residing within young, star-forming galaxies. These environments are teeming with high-energy particles, magnetic fields, and other extreme conditions that could fuel the energy release needed to produce FRBs. Magnetars, with their intense magnetic fields, are capable of storing vast amounts of energy, which could be released in powerful bursts under certain conditions. The detection of an FRB-like burst from a magnetar in our galaxy supports this theory, yet it leaves the door open to other sources, as not all FRBs fit neatly into the magnetar model. Additionally, there's the tantalizing prospect that FRBs could one day be used as standard candles, a term astronomers use for objects of known brightness used to measure cosmic distances. If scientists can identify a clear pattern or standard property among FRBs, such as their energy output, they could potentially use these bursts to calculate distances across vast cosmic scales. This would allow researchers to map the universe more accurately and probe its large-scale structure. While not yet achievable, the prospect of using FRBs as a new kind of cosmic ruler is an exciting possibility, one that could revolutionize cosmology by offering a way to study the distribution of galaxies and matter in a way that was not previously possible. FRBs also hint at the possibility of phenomena beyond our current theories of physics. Some theorists have speculated that if certain types of FRBs don't match the expected models, they could be a signal of exotic physics at work. For instance, certain high-energy FRBs might involve unknown processes related to quantum fields, black holes, or even hypotheses that lie outside standard astrophysics. Though these ideas remain speculative, they reflect the revolutionary potential of FRBs to reveal hidden aspects of the universe, particularly if future observations reveal patterns that defy existing explanations. The international effort to study FRBs reflects how seriously the scientific community is taking this mystery. From the Canadian CHIME telescope to efforts in Australia, Europe, and China, teams across the world are working to catalog, analyze, and interpret these signals. This level of collaboration underscores the importance of FRBs in modern astrophysics, as scientists from various fields contribute their expertise to understand what these strange signals mean. In some ways, the global effort to study FRBs has fostered a new era of astronomical research, where real-time data sharing, collaborative analysis, and international teamwork are central to making rapid progress. The ability to coordinate observations across different telescopes worldwide has proven especially useful, as it allows scientists to monitor regions of the sky continuously and quickly confirm new detections. Beyond the purely scientific aspects, there's an undeniable fascination with FRBs among the public. The mysterious nature of these signals, combined with the tantalizing possibility that they may represent something profoundly new in the universe, has captivated imaginations around the world. Some have even speculated on the possibility of artificial origins, imagining that advanced alien civilizations might use bursts of radio waves for communication. While there's no scientific evidence to support this idea, it speaks to the allure of FRBs as modern cosmic enigmas that provoke curiosity and wonder. The suggestion that FRBs could be messages from other intelligences, though far-fetched, adds a layer of intrigue that reflects humanity's enduring quest to find our place in the universe. The search for the origins of FRBs has also sparked innovations in observational techniques. To catch these fleeting signals, astronomers have developed specialized data processing pipelines, improved machine learning algorithms, and enhanced real-time detection systems. This technological arms race has led to the deployment of new instruments specifically designed for FRB hunting, like CHIME and the Australian Square Kilometre Array Pathfinder, a SCAP, which focus on monitoring vast swaths of the sky for short-lived events. These new tools are making it easier than ever to catch and catalog FRBs, and they promise to yield unprecedented amounts of data in the coming years, data that will be crucial for solving the FRB mystery. As more data accumulates, scientists can start to look for trends and correlations that might have been impossible to see with only a handful of detections. With hundreds and potentially thousands of FRBs in the data banks, researchers are beginning to examine whether certain types of galaxies are more likely to host FRB sources, or whether FRBs tend to be associated with specific cosmic events or environments. Patterns in the data could offer critical clues, pointing scientists toward more precise theories about what kinds of events produce FRBs. This approach mirrors the evolution of many scientific fields, where initial discoveries often seem random or isolated until enough data is collected to reveal underlying patterns. The study of fast radio bursts is more than just an investigation into a specific type of radio signal. It's a doorway into some of the most profound mysteries of the cosmos. As each new FRB is detected and analyzed, it brings with it the potential for breakthrough discoveries in fields ranging from astrophysics and cosmology to high-energy physics. FRBs are remarkable both for what they represent, extraordinary bursts of energy from across the universe, and for what they could tell us about the universe's hidden structure, extreme physics, and potentially even dark matter. The journey to unravel the FRB mystery is just beginning, and with each new observation, we edge closer to understanding one of the universe's most elusive phenomena. Yet even as we make progress, FRBs remain a stark reminder of how much we still don't know about the cosmos. They represent a thrilling frontier, one that will likely keep scientists, and the rest of us, wondering, exploring, and imagining for years to come. The story of FRBs is, in many ways, the story of scientific curiosity itself, an endless quest to understand our place in a vast and mysterious universe, where every answer leads to new questions, and every discovery reminds us of the boundless wonders that lie beyond our reach. As the study of fast radio bursts progresses, it becomes increasingly clear that they could be keys to unlocking some of the universe's deepest mysteries. The sheer variety of FRBs, ranging from single, isolated bursts to those that repeat, suggests that this phenomenon could encompass a broader spectrum of cosmic processes than initially believed. Perhaps these bursts are a cosmic symphony, produced by diverse sources that each contribute their unique notes to a larger, universal composition. Every discovery adds a new layer of complexity to our understanding, challenging existing models and pushing us to rethink what we know about the cosmos. FRBs not only offer a glimpse into potential new physical mechanisms, but also provide an opportunity to probe the interstellar medium, the gas and dust that lie between galaxies. When a fast radio burst travels through space, it interacts with this medium, which can slightly disperse and shift its signal, depending on the properties of the material it encounters. This dispersion effect can be studied to reveal details about the otherwise invisible matter between galaxies, effectively allowing FRBs to act as cosmic lighthouses that illuminate the nature and distribution of intergalactic material. Through this lens, FRBs could help map the large-scale structure of the universe in unprecedented detail. This potential use of FRBs as intergalactic probes has fueled extensive research, as scientists work to understand not just their origin, but also the journey each FRB has taken to reach us. This journey holds clues that could offer new insights into dark matter, an elusive substance that is thought to make up most of the universe's mass, yet remains invisible and undetectable except through its gravitational effects. When FRBs travel through regions thought to be rich in dark matter, they may reveal subtle distortions or delays in their signals that could help scientists infer the properties of this mysterious form of matter. Some researchers believe that as FRB detection technology improves, we could one day use these signals as a tool to locate and study dark matter in a way previously thought impossible. The relationship between FRBs and dark matter isn't the only tantalizing prospect. Some scientists have speculated that FRBs might even hint at interactions with exotic objects like primordial black holes or hypothetical cosmic strings. Primordial black holes, if they exist, are thought to have formed shortly after the Big Bang and could range widely in size and mass. If these black holes occasionally interact with other massive objects, or even collide, the energy released might result in an FRB-like signal. Though highly speculative, this idea underscores how the search for the source of FRBs could cross into areas of theoretical physics that touch upon some of the oldest, most fundamental questions about the universe's origin. Furthermore, the recent discovery of repeating FRBs has opened up even more avenues of inquiry. Repeating FRBs defy simple explanations, as they indicate a more stable, ongoing source of energy capable of producing bursts over extended periods. Unlike singular FRBs, which could be attributed to cataclysmic, one-time events like supernovae, repeating bursts suggest the involvement of a persistent, perhaps even cyclic process. This has led researchers to explore whether repeating FRBs could be associated with dense magnetar environments, or even binary systems where two massive objects orbit each other, producing bursts through complex interactions of their magnetic fields. The repeating nature of some FRBs has prompted astronomers to conduct focused studies on these sources. By observing the same FRB over multiple occurrences, scientists hope to identify any subtle changes in its frequency, intensity, or other characteristics, which might reveal details about its source. Interestingly, some repeaters exhibit periodicity, where the bursts follow a roughly predictable pattern. This characteristic further supports the idea that at least some FRBs are tied to stable, recurring cosmic events. For example, one repeater shows activity in cycles of 16 days, suggesting that it might be part of a binary star system where one of the objects emits bursts at a specific phase of its orbit. While this idea remains unproven, the study of periodic FRBs could shed light on the orbital dynamics of systems in distant galaxies, and possibly even offer a new way to observe binary interactions. One of the primary challenges in studying FRBs is their ephemeral nature. These bursts last only milliseconds, making them difficult to pinpoint in real time. Once an FRB is detected, astronomers have only a fraction of a second to record as much information as possible before the signal fades. For years, this limitation hindered efforts to trace FRBs back to their sources. However, advances in detection technology, combined with more powerful telescopes and automated data processing systems, have improved astronomers' ability to capture and analyze FRBs more effectively. The Canadian Hydrogen Intensity Mapping Experiment, CHIME, a radio telescope array specifically designed to study FRBs, has played a crucial role in advancing our understanding of these bursts. Since beginning operations, CHIME has detected hundreds of FRBs, vastly increasing the sample size available for study. Its continuous monitoring of the sky, combined with real-time data processing, has enabled it to capture FRBs at a rate never before possible. This influx of data has been invaluable for researchers, as it allows them to study FRB's statistical properties, uncovering trends and patterns that could hint at their origins. ASCAP, Australian Square Kilometre Array Pathfinder, another significant radio telescope array, has contributed further by precisely localizing some FRBs to their host galaxies. ASCAP's ability to quickly pinpoint the origins of FRBs has allowed astronomers to associate these bursts with specific types of galaxies and regions within those galaxies. For instance, some FRBs have been traced to regions of active star formation, lending support to theories that tie them to magnetars, which are often found in such environments. This localization capability is a major breakthrough, as it enables scientists to study the environments surrounding FRB sources, providing clues that might explain the conditions necessary for these powerful bursts. As telescopes and technology continue to improve, the hope is that we'll soon be able to trace many more FRBs to their origins, perhaps even identifying specific stars, black holes, or other celestial objects as their sources. Each successful localization adds to a growing map of FRB sources across the universe, gradually revealing whether there are commonalities among them that could point to their underlying mechanisms. Moreover, new facilities like the upcoming Square Kilometre Array, SKA, are expected to detect thousands of FRBs each year, potentially revolutionizing the field by providing a dataset large enough to allow for rigorous statistical analysis and comparison. In addition to observing FRBs directly, researchers are employing machine learning and artificial intelligence to sift through vast amounts of radio data in search of these elusive bursts. Machine learning algorithms are trained to recognize the specific characteristics of FRBs, allowing them to rapidly identify potential candidates from large datasets. This approach has become increasingly essential as the volume of data produced by telescopes grows exponentially. By automating the detection process, machine learning enables astronomers to capture more FRBs than would be possible with manual methods, accelerating the pace of discovery and offering a more comprehensive view of the phenomenon. As the science surrounding FRBs progresses, the field is likely to attract even greater attention from astrophysicists, cosmologists, and theoretical physicists. The potential for FRBs to bridge multiple areas of study, from the structure of the intergalactic medium to the nature of compact objects and high-energy physics, makes them an enticing target for interdisciplinary research. Each new discovery related to FRBs has the potential to redefine our understanding of the cosmos, offering insights that extend far beyond the phenomenon itself. The allure of FRBs also lies in their ability to inspire awe and wonder. They remind us of the vast unknowns that remain in our understanding of the universe, urging us to keep exploring, questioning, and seeking answers. While science may one day reveal the secrets of fast radio bursts, the journey to that discovery is likely to bring countless revelations about the nature of the universe and our place within it. With each new FRB, we inch closer to uncovering truths that have eluded humanity for millennia, truths that may reshape not only our understanding of astrophysics but also our perception of existence itself. The study of fast radio bursts serves as a profound reminder of the vast scope of what we still don't understand about the universe. FRBs seem almost like cosmic puzzles, demanding that we rethink established astrophysical theories, develop new observational techniques, and apply complex, interdisciplinary approaches to make sense of them. Each potential breakthrough in understanding FRBs, whether through improved technology, more precise localization, or advanced data analysis, promises to deepen our comprehension of everything from the behavior of matter under extreme conditions to the distribution of unseen material throughout the cosmos. One of the most tantalizing aspects of FRB research is how it has prompted scientists to revisit and refine existing models in astrophysics. Traditional astrophysics has largely revolved around well-known objects and phenomena, like stars, galaxies, black holes, and gravitational waves. FRBs, however, are different. They do not fit neatly into any of these categories, seeming instead to arise from a unique set of astrophysical circumstances. Their intense, short-lived nature suggests they are triggered by extremely energetic events, but their diversity in behavior, particularly the distinction between single and repeating FRBs, indicates that multiple mechanisms may be at play. This complexity has led to a number of intriguing hypotheses. For instance, one prevailing theory suggests that FRBs could originate from starquakes on the surface of magnetars, neutron stars with exceptionally strong magnetic fields. When the magnetic field of a magnetar undergoes a sudden reconfiguration, the energy released could create a powerful burst of radiation, potentially resulting in an FRB. This idea is supported by the fact that magnetars have already been observed producing gamma-ray and X-ray bursts, demonstrating their ability to release sudden, intense pulses of energy. Moreover, some astronomers speculate that the formation of black holes might be related to FRBs. When a massive star collapses into a black hole, the intense gravitational forces and rapid release of energy could theoretically produce a short burst of radiation that resembles an FRB. Although this theory is challenging to test due to the difficulty in observing black hole formation directly, it is one of many ideas being explored as scientists work to pinpoint the origins of these bursts. Another layer of intrigue comes from the speculation that FRBs could be signs of alien civilizations. This idea, while controversial, has sparked significant interest among the public and scientific communities alike. The logic behind this hypothesis lies in the structured, repetitive nature of some FRBs, particularly those that exhibit periodicity. If a signal repeats at regular intervals, it could theoretically indicate an intentional transmission. While there is no conclusive evidence to support this, the possibility is exciting and encourages scientists to remain open-minded. The SETI, Search for Extraterrestrial Intelligence, Institute has conducted preliminary studies to explore whether FRBs might contain any unusual patterns that could signify intelligent design, though none have been found thus far. Nonetheless, the alien hypothesis is unlikely to be the leading explanation, as natural astrophysical processes can account for many of the characteristics observed in FRBs. The diversity in FRB behavior, some repeating, some occurring only once, suggests that multiple natural sources are likely responsible. Furthermore, the enormous energies involved in generating FRBs imply that their sources are probably extreme astrophysical environments, which would be difficult to replicate artificially, even by advanced civilizations. Still, the mere consideration of FRBs as potential signals from other intelligent beings reflects humanity's fascination with the possibility of life beyond Earth. FRBs have also had a significant impact on the field of cosmology, offering a new method to study the distribution of matter throughout the universe. Because these bursts travel across vast cosmic distances, they pass through the intergalactic medium and interact with the particles within it. This interaction causes a delay in the signal, known as dispersion, which can be measured to estimate the density of electrons encountered by the FRB on its journey. By analyzing this dispersion measure, scientists can make inferences about the amount and distribution of missing matter in the universe, normal, baryonic matter that does not emit light and thus is difficult to detect directly. The potential of FRBs as cosmological probes is profound. They may enable astronomers to conduct large-scale surveys of the universe's structure, mapping the locations of gas clouds and other intergalactic features that are invisible to conventional telescopes. This ability could complement other cosmic mapping tools, like gravitational waves and cosmic microwave background radiation, creating a more comprehensive view of the universe's composition and structure. In time, FRBs could even help resolve questions about the role of dark matter and dark energy, mysterious substances that make up most of the universe's mass energy content but remain largely unobservable. Another groundbreaking avenue of research involves studying FRBs' polarization properties. Polarization refers to the orientation of the light waves that make up a radio signal. When an FRB's signal passes through a magnetic field, its polarization changes in a way that reveals information about the field's strength and structure. By analyzing the polarization of FRBs, scientists can learn more about the magnetic environments surrounding their sources. This approach is particularly useful in studying environments like those surrounding magnetars, where magnetic fields are so intense that they fundamentally alter the properties of matter and radiation in their vicinity. As research into FRBs advances, collaborations between international observatories are becoming increasingly important. The field's rapid growth has necessitated a global effort to monitor the skies continuously, as FRBs can occur at any time and last for only a fleeting moment. This global approach is crucial for building a comprehensive database of FRBs, enabling scientists to compare observations and refine their models. By pooling resources and sharing data, observatories around the world are working together to uncover the secrets of these powerful radio bursts. To handle the sheer volume of data generated by FRB research, astronomers are also turning to high-performance computing. The process of detecting and analyzing FRBs requires sifting through enormous quantities of radio data, identifying the short, faint signals that characterize these bursts. Machine learning algorithms play a critical role in this effort, enabling real-time detection and filtering of FRB candidates. As a result, the discovery rate of FRBs has accelerated, with hundreds of new detections each year, a stark contrast to the field's early days, when only a handful of FRBs were known. Looking to the future, the next generation of radio telescopes promises to revolutionize our understanding of FRBs even further. The Square Kilometre Array, SKA, a massive radio telescope network under development, is expected to become the world's largest radio observatory, capable of detecting thousands of FRBs annually. With its unparalleled sensitivity and resolution, the SKA will provide unprecedented detail on the locations, polarization, and spectral characteristics of FRBs. This data could bring us closer to identifying specific sources and understanding the mechanisms driving these bursts. In addition to the SKA, other projects, such as the Deep Synoptic Array, DSA, and the 500-meter aperture spherical telescope, FAST, are expanding humanity's ability to detect and analyze FRBs. These telescopes are pushing the limits of radio astronomy, with FAST holding the title of the world's largest single-dish radio telescope. With such powerful instruments at their disposal, astronomers are optimistic that the coming years will bring an explosion of new data on FRBs, potentially unlocking the answers to some of the biggest questions surrounding this phenomenon. In many ways, the study of FRBs embodies the spirit of exploration and curiosity that drives all of astrophysics. Each detection is a reminder of how little we know about the cosmos, as well as a testament to human ingenuity and our ability to push the boundaries of knowledge. Fast radio bursts represent a frontier in astronomy, where every discovery has the potential to reshape our understanding of the universe. Ultimately, the mystery of FRBs could reveal more than just the origins of these enigmatic bursts. It could challenge our assumptions about cosmic events, the composition of the universe, and even the limits of what is observable. Whether or not we ever uncover a definitive explanation for fast radio bursts, the quest to understand them is likely to inspire generations of astronomers, physicists, and dreamers, urging humanity to keep looking up and asking the unanswerable questions. The journey to uncover the truth about fast radio bursts is emblematic of the endless quest to decode the unknown mysteries of the universe. Each FRB represents a question mark on our cosmic map, urging scientists to reevaluate what they know about the interplay of extreme forces, distant galaxies, and the nature of space itself. The signal's fleeting appearance, paired with their extraordinary strength, challenges even the most seasoned astrophysicists, pushing the limits of both theory and technology. The fact that these bursts travel billions of light years before reaching Earth only adds to the mystery, as they carry with them an ancient story, one that started long before our solar system even formed. Scientists speculate that by understanding FRBs, we could gain insight into the environments of their origin, which could range from supernovae remnants and the chaotic regions around black holes to galaxies saturated with dark matter. The idea that FRBs might serve as cosmic signposts, highlighting areas of high-energy phenomena, continues to drive astronomers to monitor them closely. The analysis of each FRB brings us closer to understanding the processes occurring in the distant, tumultuous corners of space. A particularly exciting development in FRB research is the realization that some bursts repeat, while others do not. Repeating FRBs offer a unique opportunity for scientists to observe the same source multiple times, which could yield insights into the nature and structure of these objects. In contrast, one-time FRBs present a separate challenge. Their single appearance leaves scientists with no opportunity for follow-up observation, forcing them to rely on indirect clues from the signal itself. This division between repeaters and one-off bursts suggests that they might originate from different kinds of sources, or that certain conditions within a source allow for multiple bursts, while others result in only one powerful release of energy. Each time astronomers capture a repeating FRB, they eagerly await the next burst, refining their theories with every observation. One well-studied example of a repeating FRB is FRB 121102, discovered in 2012. Over the years, this FRB has been observed emitting numerous bursts, allowing scientists to pinpoint its location to a small galaxy about 3 billion light-years away. The presence of such a high number of bursts from a single source has led to a flurry of theoretical modeling, with many scientists suggesting that FRB 121102 may be associated with a highly active, magnetar-rich environment, or that it might reside in the accretion disk of a supermassive black hole, where intense gravitational forces could cause intermittent releases of radio waves. Meanwhile, new FRBs are being discovered at a rapid pace, with advanced telescopes detecting hundreds of them each year. Observatories like CHIME, the Canadian Hydrogen Intensity Mapping Experiment, have transformed FRB detection rates, capturing bursts almost daily. CHIME's unique design allows it to scan large portions of the sky, making it ideal for catching fast and transient events like FRBs. By cataloging a vast array of FRBs, CHIME and similar observatories provide a rich dataset for researchers, who can then compare these signals to identify patterns and classify bursts into potential types. As more FRBs are detected, astronomers are beginning to notice subtle differences between them, such as variations in pulse width, spectral features, and even polarization properties. These details, though minor, are critical for distinguishing between possible sources. For instance, an FRB with a broad spectrum might indicate a source undergoing a cataclysmic event, while a highly polarized burst might suggest the influence of strong magnetic fields. The immense variety in FRB characteristics hints at a complexity that is only beginning to be understood, suggesting that what we refer to as FRBs might actually encompass multiple phenomena with different causes. The potential uses of FRBs extend beyond just understanding their sources. They could also help scientists probe the properties of the universe itself. Because FRBs travel such vast distances, they interact with the intergalactic medium, the sparse, mysterious space between galaxies. As an FRB's signal passes through this medium, it encounters free electrons and other particles, causing a dispersion effect that slightly delays different frequencies of the signal. This dispersion measure provides a rough estimate of the electron density along the path of the FRB, which could help astronomers map the distribution of matter across cosmic scales. Furthermore, FRBs may provide a way to test aspects of general relativity and other fundamental physics theories. The speed of light is constant according to Einstein's theory of relativity, but certain alternative theories of gravity suggest slight deviations under extreme conditions. By carefully measuring the arrival times of FRBs across various frequencies, scientists could detect any potential deviations from the expected behavior of light, which would challenge our current understanding of physics. In this way, FRBs might help bridge the gap between quantum mechanics and general relativity, two fields that have yet to be fully reconciled. FRB research is also beginning to make use of artificial intelligence and machine learning. Given the enormous volume of data generated by radio telescopes scanning the skies, manually identifying FRBs is impractical. Instead, machine learning algorithms are trained to recognize the distinct signature of an FRB, its short duration, rapid rise and fall, and specific frequency dispersion. These algorithms can sift through vast datasets to find potential FRB candidates in real time, significantly speeding up the discovery process. Moreover, AI tools can classify and sort FRBs based on their characteristics, helping scientists discern subtle patterns that might go unnoticed by human analysts. The public's fascination with FRBs also reflects a broader curiosity about the unknown, particularly as it relates to the possibility of alien life. Though the idea that FRBs could be signals from extraterrestrial civilizations is speculative, it taps into a timeless desire to find other intelligent beings in the cosmos. Projects like Breakthrough Listen, an initiative dedicated to searching for signs of intelligent life, have scanned known FRB sources for any patterns that might hint at intentional signals. While no evidence of alien involvement has been found, the search itself is a testament to humanity's enduring quest for companionship in the universe. As research progresses, scientists are increasingly optimistic about uncovering the secrets behind FRBs. Each observation brings us closer to identifying their origins, and each discovery invites new questions about the forces shaping the cosmos. The possibility that FRBs could be a unique tool for mapping the intergalactic medium or testing the limits of fundamental physics is an exciting prospect, hinting at applications beyond what we can currently imagine. In the coming years, as the capabilities of radio telescopes continue to improve, and as computational methods become even more sophisticated, the study of FRBs is likely to reveal insights that extend far beyond the bursts themselves. We may discover new classes of cosmic events, uncover unknown properties of neutron stars and black holes, or even reshape our understanding of gravity and spacetime. Fast radio bursts represent a frontier in science, a place where every new piece of data has the potential to open up entirely new realms of understanding. Ultimately, FRBs remind us of the vast mysteries that remain hidden in the universe. They are symbols of both our progress and our limitations as we strive to comprehend the cosmos. The more we learn, the more questions we encounter, reinforcing the sense that we are only at the beginning of our journey through the stars. Yet, with each discovery, we edge closer to the answers, driven by the same spirit of exploration that has defined humanity's story for centuries. The journey to unravel the mystery of fast radio bursts, FRBs, is one of the most thrilling pursuits in modern astrophysics. These brief but immensely powerful signals challenge us to look beyond our current understanding of the universe, urging astronomers and physicists alike to develop new theories and techniques to capture every detail. While the discovery of FRBs is a relatively recent event in the history of science, their significance has quickly captured the attention of the scientific community and the public alike, reminding us that the universe still holds countless secrets waiting to be uncovered. One of the most astonishing aspects of FRBs is the sheer amount of energy they release in such a short span of time. To put it into perspective, a single FRB emits as much energy in a millisecond as the sun emits in an entire day. This immense power packed into such a fleeting event suggests a highly energetic source, likely involving some of the most extreme environments and processes in the cosmos. The fact that FRBs are detectable across billions of light-years further underscores their magnitude, as their signals travel vast cosmic distances, enduring interactions with interstellar and intergalactic media before finally reaching Earth. The study of FRBs has already led to profound implications about the structure and contents of the universe. For example, FRB signals undergo dispersion as they travel through space, meaning different frequencies of the burst arrive at slightly different times. This dispersion provides scientists with a valuable tool for measuring the density of electrons along the path of the FRB, effectively allowing them to see the otherwise invisible matter scattered across the universe. This is particularly significant when we consider that most of the matter in the universe is thought to exist as diffuse gas between galaxies, matter that is difficult to observe directly with traditional methods. By studying FRBs, researchers are able to probe this elusive material, gradually piecing together a more complete picture of the cosmos. Moreover, the observation of FRBs has had a ripple effect across various branches of physics and astronomy, sparking new theories and reshaping existing ones. Many scientists speculate that FRBs could provide a unique laboratory for studying the nature of magnet-Rs, neutron stars with extraordinarily strong magnetic fields. Magnet-Rs are known to produce intense magnetic storms and bursts of radiation, and it is thought that some of these events could be responsible for the FRBs we detect. If this theory is correct, FRBs could serve as a window into the behavior of matter and energy under the influence of magnetic fields that are trillions of times stronger than those we can produce on Earth, offering insights that could be applied to fields ranging from particle physics to quantum mechanics. Another possibility is that some FRBs may originate near black holes, where extreme gravitational forces and complex interactions between matter and energy could produce the conditions necessary for these bursts. Black holes are often surrounded by accretion disks, rings of superheated gas and dust pulled toward the black hole by its gravity. In these environments, matter can be compressed to extraordinary densities, releasing large amounts of energy. The idea that FRBs could originate from these turbulent regions opens up exciting possibilities for studying the environments around black holes in new ways. If we can determine the precise locations of FRBs and confirm that some are near black holes, it might help us understand how black holes interact with their surroundings, shedding light on some of the most enigmatic objects in the universe. The diversity of FRBs, ranging from those that appear only once to those that repeat with varying degrees of regularity, further complicates the quest for a unified explanation. The discovery of repeating FRBs, such as FRB 121102, was a major turning point in FRB research, demonstrating that not all bursts are singular events. Repeating FRBs have allowed astronomers to monitor specific sources over time, revealing patterns and providing opportunities to study these phenomena in much greater detail. By tracking repeating FRBs, scientists can gather information about the physical conditions and processes that lead to multiple bursts, which may differ from the conditions that produce one-time FRBs. This distinction could imply that FRBs have multiple sources or that certain environments enable repeated emissions. One particularly intriguing aspect of repeating FRBs is the discovery of periodic activity cycles in some of these sources. In recent years, astronomers have identified FRBs that exhibit regular bursts over periods of time, such as FRB 180916, which follows a roughly 16-day cycle. For 4 days, this source emits bursts, then goes silent for 12 days before starting the cycle anew. This periodic behavior suggests that the source of the FRB might be part of a binary system, possibly orbiting a massive object like a black hole or another neutron star. The gravitational influence of such an object could lead to bursts being emitted at regular intervals, as the source moves closer or farther from its companion in its orbit. If this theory is correct, it could provide new insights into the dynamics of binary systems and the interactions between closely orbiting celestial bodies. The quest to understand FRBs has also inspired scientists to develop and implement cutting-edge technology in observational astronomy. Advanced radio telescopes like the Canadian Hydrogen Intensity Mapping Experiment, CHIME, have been pivotal in the discovery and cataloging of FRBs, with CHIME alone detecting hundreds of new bursts since it began operations. CHIME's unique design allows it to scan vast portions of the sky simultaneously, making it particularly effective at capturing transient events like FRBs that appear unexpectedly and last only a few milliseconds. Other observatories, such as the ESCAP telescope in Australia and the Deep Synoptic Array in California, have also contributed to FRB research, each offering unique capabilities that help astronomers refine their data and gain new perspectives on these phenomena. These technological advancements are complemented by the growing role of artificial intelligence and machine learning in FRB research. The massive data output generated by telescopes like CHIME requires sophisticated tools to process and analyze, and machine learning algorithms have proven invaluable in this context. By training AI systems to recognize the distinct characteristics of FRBs, researchers can sift through vast amounts of radio data, identifying new FRB candidates with unprecedented speed and accuracy. Machine learning algorithms can also assist in classifying FRBs based on their properties, helping scientists identify potential subcategories of bursts that might correspond to different types of sources or mechanisms. While the scientific community remains cautious about the possibility of extraterrestrial origins for FRBs, the public fascination with this idea underscores the broader implications of the mystery. The sheer unpredictability and intensity of FRBs have led some to speculate that they might be deliberate signals from advanced civilizations, although no evidence supports this hypothesis at present. Nevertheless, the search for extraterrestrial intelligence, SETI, initiatives have included FRBs in their observations, exploring the possibility, however remote, that these bursts could carry encoded messages or patterns indicative of intelligent design. Even though the focus of most FRB research is firmly rooted in natural explanations, the idea that they could serve as beacons from alien societies remains a tantalizing notion, reflecting humanity's enduring hope of making contact with other forms of life in the universe. The study of FRBs is also significant in the context of cosmology, as these bursts could help answer fundamental questions about the structure and expansion of the universe. Since FRBs are detectable across vast distances, they could serve as probes of the cosmos, illuminating the distribution of matter and energy on a grand scale. Some scientists suggest that FRBs could even be used to test the Hubble constant, a measure of the rate at which the universe is expanding, by comparing the distances of various FRBs to their dispersion measures. Such an approach might provide an independent check on the value of the Hubble constant, potentially resolving discrepancies between different measurements and refining our understanding of cosmic expansion. Looking ahead, the future of FRB research appears bright, with new telescopes and observation networks poised to unlock even more mysteries surrounding these enigmatic bursts. The Square Kilometre Array, SKA, currently under development, is expected to revolutionize radio astronomy, with a sensitivity and resolution far surpassing that of any current telescope. Once operational, the SKA could detect thousands of FRBs annually, capturing even fainter signals from deeper within the universe. This would allow scientists to trace FRBs across greater distances and gain a more comprehensive view of their distribution and properties. By mapping FRBs in this way, researchers could deepen their understanding of the universe's large-scale structure and perhaps even uncover new classes of cosmic phenomena. In many ways, FRBs represent the frontier of scientific discovery, reminding us of the vast unknowns that lie beyond our current knowledge. They are cosmic puzzles that demand innovative thinking, advanced technology, and interdisciplinary collaboration. Each discovery in FRB research brings with it new questions, new theories, and a renewed sense of wonder at the complexities of the universe. Just as the discovery of pulsars transformed our understanding of neutron stars, so too might the study of FRBs unlock new insights into the most extreme environments in the cosmos, and perhaps even challenge our most fundamental assumptions about the nature of reality. In the grand tapestry of the universe, FRBs are threads of mystery and discovery, pointing toward realms of knowledge that humanity has only just begun to explore. Whether they originate from magnetars, black holes, or some as yet unknown process, FRBs will continue to captivate scientists and the public alike, inviting us to look up into the night sky with curiosity and awe. The journey to understand FRBs is more than just a quest for scientific knowledge. It is a testament to humanity's unyielding desire to comprehend the cosmos and our place within it. And as we continue this journey, one thing is certain: the mystery of fast radio bursts will remain one of the most compelling and inspiring challenges of 21st century astrophysics. The phenomenon of fast radio bursts, FRBs, has ushered in a new era of cosmic inquiry, as scientists use these fleeting signals to probe some of the most distant and enigmatic regions of the universe. The very nature of these bursts, rapid, intense, and extraordinarily powerful, demands technological and analytical advancements on a scale that pushes the boundaries of current science. In recent years, the pace of FRB discoveries has accelerated, thanks largely to innovations in telescope technology, sophisticated data analysis methods, and collaborative global research efforts. One fascinating aspect of FRB research is the way it intersects with the field of high-energy astrophysics. While traditional astronomy has primarily focused on observing light in the visible spectrum, FRBs exist far beyond the capabilities of optical telescopes, requiring radio observatories to capture their unique signatures. The development of ultra-sensitive radio telescopes has opened new doors in this respect, enabling scientists to detect and analyze even the briefest and faintest of these signals. Observatories like CHIME, the Arecibo telescope before its collapse, and now new arrays under development, have been pivotal in identifying and cataloging FRBs, each contributing invaluable data that helps to refine our understanding of the underlying mechanisms behind these bursts. In particular, CHIME's success has been transformative, uncovering hundreds of FRBs and substantially increasing the sample size that scientists have to work with. The continuous stream of data from CHIME has made it possible to identify new FRBs almost daily, providing researchers with a rich dataset to study patterns, repetitions, and anomalies within FRB signals. Some FRBs exhibit polarization, a property that reveals information about the magnetic fields they pass through. By analyzing this polarization, scientists gain insights into the magnetic environments in which these bursts occur, and the intergalactic medium they travel through on their way to Earth. Polarization in FRBs has significant implications for our understanding of magnetars, which are among the prime candidates for FRB sources. Magnetars are unique in their extreme magnetic fields, which are strong enough to warp the space around them. These intense fields produce radiation that can be observed as bursts in the radio spectrum. In studying the polarization patterns of FRBs, scientists can indirectly observe these magnetic fields, allowing for a better grasp of the behaviors of magnetars under different conditions. If magnetars are indeed responsible for at least some of the FRBs detected, this would mark an extraordinary step forward in our understanding of how these cosmic phenomena operate. One of the major challenges in studying FRBs is pinpointing their exact locations. For an FRB observed from Earth, it's only visible for a fraction of a second, and pinpointing a precise origin within a distant galaxy is extremely difficult. However, the breakthrough came with localized FRBs, such as FRB 121102, the first repeating FRB to be traced to a specific galaxy in 2017. Located in a dwarf galaxy approximately 3 billion light-years away, this FRB provided a crucial piece of the puzzle, suggesting that its origin might lie in a unique environment capable of producing such high-energy bursts. The localization of FRB 121102 has spurred efforts to map other FRBs in a similar way, though each detection is a monumental challenge requiring specialized equipment and international collaboration. The process of localizing FRBs relies on a technique called interferometry, where multiple telescopes work together to triangulate the position of an FRB based on slight time differences in when they detect the signal. This method has allowed astronomers to narrow down the origins of a few FRBs to specific galaxies and, in some cases, even specific regions within those galaxies. This level of precision offers unprecedented insights into the potential environments where FRBs originate, revealing details about the types of stars, magnetic fields, and gas clouds that might be involved in their creation. Adding another layer to the mystery, some localized FRBs have been found in locations that defy expectations. Rather than originating from active star-forming regions or the centers of galaxies, locations often associated with high-energy events, some FRBs have been traced to the outskirts of galaxies or regions with relatively low star formation. These unusual placements challenge the magnetar hypothesis and open the door to alternative theories, such as interactions involving black holes, white dwarfs, or even exotic phenomena not yet fully understood. Each new localization presents a unique case study that either supports or questions existing models, highlighting the diversity and complexity of FRB sources. The diversity of FRB properties has also raised the possibility that there might be different classes of FRBs, each with its own unique characteristics and origins. Some researchers propose that there are at least two main types, repeating and one-off FRBs. While repeating FRBs suggest a source capable of emitting bursts multiple times, perhaps due to an ongoing process or cyclical event, one-off FRBs might represent cataclysmic events that destroy the source in the process, such as the collapse of a neutron star or a massive stellar explosion. If these two classes indeed exist, they would point to fundamentally different physical mechanisms, each requiring distinct astrophysical models to explain. This hypothesis of multiple FRB types has fueled interest in studying FRBs across a range of wavelengths, including X-rays and gamma rays. If certain FRBs are associated with high-energy events, it stands to reason that they might also emit radiation in these other parts of the spectrum. By observing FRBs at multiple wavelengths, scientists can search for correlations and gain a more complete picture of the events surrounding each burst. This multi-wavelength approach could help verify whether FRBs are tied to processes like supernovae, gamma-ray bursts, or even the merging of compact objects like neutron stars and black holes, which are known to produce powerful bursts of radiation. Another intriguing dimension of FRB research is the potential to use these signals as cosmic lighthouses, helping to map the missing matter in the universe. According to our understanding of cosmology, the observable universe contains far less visible matter than the total matter predicted by theoretical models. Scientists suspect that much of this missing matter exists as dispersed gas between galaxies, difficult to detect through conventional means. Because FRBs travel vast distances, they pass through and interact with this intergalactic medium, and their signals are affected by the electron density of the medium they traverse. By analyzing the dispersion of FRB signals, researchers can indirectly measure the amount of this otherwise elusive matter, offering a novel method for mapping the universe's missing mass. This application of FRBs as cosmic probes is especially exciting, as it promises to provide data that could reshape our understanding of the large-scale structure of the universe. If scientists can establish a reliable model for how FRB signals interact with intergalactic matter, they could use FRBs to trace the distribution of gas and other materials on a cosmic scale, creating a more detailed map of the universe. Such a map could answer fundamental questions about the composition of the cosmos, the behavior of dark matter, and the processes that drive the formation and evolution of galaxies. In addition to their potential as cosmic probes, FRBs also present a unique opportunity to test theories related to fundamental physics, including the limits of relativity and the behavior of light under extreme conditions. The distances traveled by FRBs mean that even minute effects of space-time curvature, gravitational fields, and other phenomena accumulate over billions of light years, making FRBs an effective tool for testing general relativity and other aspects of gravitational theory. By examining how FRBs propagate across space and time, scientists can investigate whether the laws of physics remain constant across cosmic distances, a question with profound implications for our understanding of the universe. FRBs have also attracted interest from researchers studying quantum mechanics, and the nature of reality itself. Some theories suggest that the space through which FRBs travel is not a smooth continuum but may instead have a granular or foamy structure at quantum scales. As FRBs pass through this quantum foam, their signals could theoretically exhibit tiny distortions, detectable with highly sensitive instruments. Observing such distortions would provide evidence supporting certain interpretations of quantum mechanics and potentially reveal new insights into the fabric of spacetime. On the more speculative end, the possibility of FRBs as artificial signals, created by extraterrestrial civilizations, has captivated the imagination of both scientists and the public. While there is no concrete evidence to suggest that FRBs are intentionally generated, the sheer energy and consistency of these signals have led some to consider the idea that they could be engineered for long-distance communication. SETI researchers, who search for extraterrestrial intelligence, have included FRBs in their investigations, although they maintain a healthy skepticism, focusing instead on natural explanations. Nonetheless, the remote possibility that FRBs could represent a form of intergalactic messaging adds an element of intrigue, underscoring the broader human desire to connect with other intelligent beings. As the hunt for answers continues, the field of FRB research stands as a testament to the collaborative nature of modern science. With international observatories and interdisciplinary teams working around the clock, each new discovery adds a piece to the puzzle, gradually expanding our understanding of these phenomena. The combination of advanced technology, theoretical innovation, and global teamwork is paving the way for breakthroughs that could redefine our understanding of the universe in ways we cannot yet imagine. In essence, FRBs are more than just bursts of radio waves. They are cosmic mysteries that inspire both awe and curiosity. Their study touches on nearly every aspect of astrophysics, from the behavior of extreme environments to the distribution of matter across the universe. As we probe deeper into the nature of FRBs, we are likely to uncover answers that not only explain these bursts but also raise new questions about the nature of reality itself. And in this sense, the mystery of FRBs is a reminder that, in the grand cosmic scheme, we are still very much explorers at the edge of knowledge, guided by the light of the unknown. The enigma of fast radio bursts, FRBs, doesn't just lie in the signals themselves, but in the tantalizing possibilities they represent. At their core, FRBs challenge our understanding of high-energy astrophysics, providing both a profound mystery and a rare observational opportunity. Each burst offers a glimpse into extreme cosmic environments, likely involving entities with unimaginable energy levels, yet with origins that remain frustratingly elusive. The nature of these bursts has sparked intense debate across the scientific community, with multiple competing theories vying for attention, each one pushing our understanding of astrophysical processes further. One of the biggest mysteries surrounding FRBs is why certain bursts repeat, while others appear as isolated, one-time events. Repeating FRBs, like the well-studied FRB 121102, allow for extensive observation, which is crucial for unraveling the physics behind them. For example, by studying the intervals, patterns, and slight variations in the strength and duration of repeated bursts, scientists have been able to make educated guesses about the possible causes. The notion that these repeating FRBs may be associated with certain types of neutron stars or magnet-ars has gained traction, particularly given that magnet-ars possess powerful magnetic fields capable of producing the high-energy emissions observed in FRBs. However, the irregular nature of these repeats remains difficult to explain. No two bursts are identical, and the intervals can vary unpredictably. The isolated, non-repeating FRBs, on the other hand, pose a different set of questions. Without recurring signals, scientists have fewer observational opportunities, and thus limited data, which makes it challenging to draw conclusions about their sources. The idea that one-off FRBs could result from catastrophic events, such as the collision of neutron stars, black holes, or other high-energy cosmic collisions, has become a compelling explanation. Such events would produce powerful, one-time bursts, but destroy the source in the process, explaining why they do not repeat. This potential connection between FRBs and events like neutron star mergers could link FRBs to gravitational waves, which are also produced by these collisions. By studying both phenomena in tandem, researchers might gain a new tool for exploring high-energy astrophysical events on a deeper level. Interestingly, the study of FRBs has also led to unexpected insights into galactic structures and the cosmic web, the vast network of gas, dark matter, and galaxies that span the universe. When an FRB travels through space, it passes through various clouds of gas and other matter that alter its signal. This process, called dispersion, provides scientists with valuable data about the composition of the regions the signal traverses. For example, the way an FRB's signal is delayed, or stretched, as it passes through different materials can reveal information about the density and type of matter present in intergalactic space. By compiling data from multiple FRBs, astronomers are beginning to map out the otherwise invisible matter in the cosmic web, shedding light on the universe's large-scale structure and the distribution of matter. The relationship between FRBs and magnetars is another area of intense investigation. Magnetars are highly magnetized neutron stars, and they represent some of the most extreme environments in the known universe. In recent years, evidence has mounted that certain types of FRBs might indeed originate from magnetars. For instance, a notable FRB detected in our own galaxy, the Milky Way, in April 2020 was associated with a known magnetar, SGR 1935+2154. This local FRB provided scientists with a rare opportunity to observe an FRB from within the Milky Way, offering crucial data that strongly supports the magnetar hypothesis. The strength and pattern of this Milky Way FRB closely mirrored those of extragalactic FRBs, suggesting that at least some FRBs from distant galaxies could be produced by similar magnetars. Yet, the magnetar hypothesis doesn't fully solve the FRB puzzle. Not all FRBs fit neatly into the magnetar model, and some FRBs exhibit characteristics that seem inconsistent with this explanation. For instance, certain FRBs have energy levels that far exceed what typical magnetars are believed to produce. These superbright FRBs hint at the possibility of alternative or additional sources. The quest to identify what these other sources might be has led scientists to propose a range of exotic theories, from binary star systems with unusual characteristics to completely new types of cosmic phenomena that have yet to be discovered or understood. As researchers delve deeper into these mysteries, they are also exploring the potential for FRBs to act as beacons that could aid in probing the early universe. Since FRBs are incredibly bright and can be detected across billions of light years, they serve as convenient markers for studying cosmic distances and the state of the universe at different points in time. By analyzing FRBs from various points in the universe, astronomers might gain insights into how cosmic conditions have evolved over billions of years. For instance, the dispersion of FRB signals over time can reveal changes in the density and composition of the intergalactic medium, offering a way to look back at the universe's history and perhaps even detect events from the epoch of reionization, the period shortly after the Big Bang when the first stars and galaxies formed. Another particularly compelling theory suggests that FRBs could serve as a tool for investigating dark matter, the mysterious substance that makes up most of the universe's mass. While dark matter does not emit, absorb, or reflect light, it does have gravitational effects, which can bend or alter the path of FRB signals. By studying slight variations in the pathways of FRBs, researchers might be able to map the distribution of dark matter, even in the absence of direct observational data. This method could allow scientists to identify regions of space where dark matter is especially dense, opening a new frontier for studying one of the universe's most persistent mysteries. The applications of FRBs as probes of fundamental physics also extend to testing the limits of Einstein's theory of general relativity. General relativity has withstood countless experimental tests, but extreme conditions, such as those present in the environments that produce FRBs, could reveal deviations or limitations in the theory. For example, if FRB signals pass near extremely massive objects, the signals would experience gravitational lensing, a bending of light due to gravity predicted by general relativity. Analyzing such distortions could confirm or challenge our understanding of gravity on cosmic scales. Similarly, the vast distances that FRBs travel provide a unique context for studying whether the speed of light remains constant over billions of years, as predicted by relativity. Finally, we cannot discuss FRBs without addressing the ongoing, albeit speculative, consideration of alien technology. The idea that FRBs might be artificially produced by advanced extraterrestrial civilizations has captured the public's imagination and sparked scientific debate. While most researchers maintain that natural explanations are more plausible, the characteristics of FRBs, such as their brightness, energy levels, and precise frequencies, do leave room for speculation. Some scientists, notably those involved in the search for extraterrestrial intelligence, SETI, have suggested that certain FRBs could potentially be signals from advanced civilizations attempting to communicate or power their technologies. Although there is no definitive evidence to support this idea, it remains an area of interest that pushes the boundaries of traditional scientific inquiry. The study of fast radio bursts continues to challenge and redefine our understanding of the universe, demonstrating the limits of current astrophysical models and inviting exploration into realms of science yet uncharted. Each discovery prompts new questions, and each new FRB detection reveals a piece of a vast cosmic puzzle. As we look to the future, the potential for new observatories and more advanced technology holds the promise of further unraveling the mystery of FRBs. The next generation of radio telescopes, such as the Square Kilometre Array, SKA, is expected to deliver unprecedented sensitivity and range, potentially detecting thousands more FRBs and providing the data needed to refine or even revolutionize existing theories. In many ways, FRBs exemplify the thrill and mystery of cosmic exploration. These fleeting signals are not just astronomical curiosities. They are profound reminders of how much remains unknown about the universe. As scientists continue to listen to the cosmos, deciphering each burst, they inch closer to unlocking the secrets of one of the most enigmatic phenomena in astrophysics. Whether FRBs turn out to be signals from magnetars, evidence of dark matter, or even, however unlikely, a distant call from an advanced civilization, they remind us that the universe is a vast, complex, and ultimately mysterious place, full of surprises yet to be discovered. The discovery of more FRBs, especially through upcoming advancements in telescopic technology, will be crucial in piecing together the vast puzzle these signals present. Telescopes like the Square Kilometre Array, SKA, and the Canadian Hydrogen Intensity Mapping Experiment, CHIME, are set to play groundbreaking roles in the ongoing study of FRBs. With SKA's extraordinary sensitivity, scientists expect to be able to detect thousands, if not millions, of FRBs each year. This volume of data could reveal patterns and trends that were previously undetectable, shedding new light on the origin and nature of FRBs. CHIME, although already operational, represents a massive leap in FRB observation and detection. Situated in Canada, CHIME is uniquely suited for capturing FRBs, as it constantly scans a huge portion of the sky, unlike traditional telescopes which focus on smaller areas. Since coming online, CHIME has contributed significantly to the identification of new FRBs, especially by detecting repeating bursts that allow for long-term study. These ongoing detections could help astronomers address questions about the difference between one-off and repeating FRBs, potentially identifying what makes certain bursts recur. Beyond SKA and CHIME, a host of other instruments are enhancing FRB research. For example, China's 500-meter aperture spherical radio telescope, FAST, the world's largest single-dish radio telescope, has detected and analyzed numerous FRBs with high precision. FAST's massive size allows it to capture details that smaller telescopes might miss, and it has already identified some of the most powerful FRBs known to date. Together, these observatories form an increasingly sophisticated global network, each adding critical pieces to the FRB puzzle. One promising area of research made possible by this wealth of new data is the FRB host galaxy investigation. By identifying the galaxies from which FRBs originate, scientists can examine the environments where these bursts are produced, providing clues about their sources. Most FRBs seem to originate in galaxies rich in star formation, which suggests that young, massive stars or remnants like magnetars might be involved. However, there are exceptions, with some FRBs originating from galaxies with low star formation rates, which complicates the story and suggests that multiple types of sources could be responsible for FRBs. The sheer diversity among FRBs, varying in intensity, duration, and frequency, has led researchers to hypothesize that they might not all come from a single type of event or object. Instead, there could be multiple sources of FRBs, each producing a distinct type of burst. For instance, magnet ARs might account for certain types of repeating FRBs, while neutron-star collisions or black hole mergers could explain intense, one-off bursts. If this hypothesis holds, it means FRBs could be a more complex category of phenomena than originally thought, encompassing a range of high-energy astrophysical processes. Another intriguing aspect of FRBs is how their signals might allow scientists to study previously undetectable structures in the universe, particularly those associated with dark matter. As FRBs travel through space, their paths and frequencies are subtly altered by the gravitational pull of matter they encounter. By analyzing these alterations, scientists can map the missing matter in the universe, including dark matter, which neither emits nor reflects light and can't be directly observed. Studying these changes might eventually reveal the structure and distribution of dark matter, potentially resolving one of the greatest mysteries in astrophysics. Furthermore, FRBs offer unique insights into the fundamental physics of the universe. For example, the observation of time delays between different frequencies of an FRB can provide clues about the strength and composition of magnetic fields between galaxies. Scientists can measure this delay to estimate the density and ionization levels of intergalactic space, which in turn helps refine models of cosmic evolution. By understanding these magnetic fields, researchers gain a window into conditions in the early universe and the processes that shaped galaxy formation. The precision of FRB measurements also allows astrophysicists to test the limits of the laws of physics, particularly regarding the invariance of physical constants. For instance, if the speed of light or the behavior of electromagnetic waves were to vary over vast cosmic distances, FRBs would be among the phenomena most likely to reveal such discrepancies. So far, observations of FRBs have supported the constancy of these physical laws, which is significant for confirming our current models of physics. However, as detection techniques improve, even small anomalies could suggest that our understanding of the universe's fundamental laws needs to be updated. FRBs are not only expanding our knowledge of high-energy astrophysics but also influencing discussions about extraterrestrial intelligence. Although natural explanations are far more likely, the concept of FRBs as potential signals from advanced civilizations persists, partially because of the structured, high-frequency nature of the bursts. The speculative beacon hypothesis posits that these bursts could be artificial in origin, intentionally created by extraterrestrial technology to broadcast signals over vast distances. While no definitive evidence supports this theory, it adds a layer of fascination to FRB studies and reminds us that the search for extraterrestrial intelligence, SETI, is an ever-present element of radio astronomy. The implications of understanding FRBs extend far beyond astrophysics, potentially reshaping the way we perceive our place in the universe. By investigating these rapid signals, we learn more about the nature of cosmic evolution, the forces that shape the universe, and the complex processes that govern distant galaxies. Each new discovery about FRBs adds depth to our understanding of the cosmos, even as it raises new questions. As our observational tools and analytical methods improve, we might one day find that FRBs serve as a cosmic Rosetta Stone, helping us interpret the vast and varied signals the universe sends our way. As research continues, international collaboration will be essential. The mystery of FRBs has inspired a global scientific effort, bringing together teams of astronomers, data scientists, and physicists from around the world. This collaboration has led to a pooling of resources, sharing of data, and development of advanced techniques for interpreting FRB signals. It exemplifies how modern astrophysics relies on cooperation, where large-scale discoveries can only be achieved through joint efforts that cross national and disciplinary boundaries. Each new breakthrough in FRB research reflects the immense progress that has been made in understanding the universe, even as it underscores the profound gaps in our knowledge. The continued study of FRBs will undoubtedly lead to new theories, new insights, and possibly even revolutionary shifts in our perception of space and time. As we probe deeper into these cosmic mysteries, we find ourselves not only answering questions about distant galaxies but also uncovering fundamental truths about existence itself. The study of fast radio bursts remains one of the most captivating frontiers in astrophysics, a field where every new observation has the potential to upend established theories and inspire new avenues of inquiry. As technology advances and our observational capabilities expand, it's only a matter of time before we uncover more of the secrets hidden in these powerful, enigmatic bursts. Yet, for now, each FRB continues to serve as a reminder of the vast and largely unexplored cosmic landscapes that lie beyond our current understanding, beckoning humanity to reach further into the unknown. The continuous study of fast radio bursts stands as a testament to the boundless curiosity that drives humanity's exploration of the cosmos. With every new FRB detection, scientists take a step closer to unmasking the complex and hidden dynamics of the universe, refining our understanding of everything from cosmic structures to the behavior of matter under extreme conditions. These fleeting radio signals, which blaze for just milliseconds before fading, may seem insignificant on the cosmic scale, yet they have already revealed a great deal about the environment between galaxies, the properties of dark matter, and even the possible existence of exotic cosmic objects that defy current understanding. In recent years, the study of FRBs has spurred the development of sophisticated methods for tracking and analyzing astronomical signals. Machine learning, for instance, is now an essential tool in this field, allowing scientists to sift through vast amounts of data to identify and characterize FRB signals with remarkable accuracy. Artificial intelligence has also enabled researchers to pinpoint patterns within FRB bursts that may hold critical clues about their origins. By identifying recurrent features in these patterns, researchers can test hypotheses regarding the mechanisms driving these energetic explosions, from theories involving dense stellar remnants like neutron stars to those suggesting new and unimagined phenomena. At the same time, FRB research is fostering a deeper exploration of intergalactic space, regions so remote and sparse that they were once thought to hold little significance. Each FRB signal traverses these vast stretches, interacting with the thin plasma clouds that permeate intergalactic space. As the radio waves from an FRB pass through these clouds, they experience slight delays based on the density and structure of the medium. By measuring these delays, scientists are able to map out these elusive regions, revealing their density, composition, and even the distribution of matter on scales previously beyond our reach. This mapping capability holds incredible potential for the study of dark matter, which is believed to comprise about 85% of the universe's matter. Because dark matter does not emit, absorb, or reflect light, it cannot be observed directly. However, by analyzing how FRBs interact with dark matter's gravitational influence, researchers can indirectly measure its effects. In this way, FRBs act as cosmic probes, allowing scientists to see dark matter in action and gain valuable insights into its distribution and properties. Each FRB detected brings us closer to understanding the mysterious substance that exerts such a profound influence on the structure and evolution of the cosmos. One particularly intriguing aspect of FRB research is the possibility that these signals could one day be used as an astrophysical tool for measuring distances across the universe. Unlike other methods that rely on brightness or redshift, FRBs could offer a new, highly precise way of gauging cosmic distances based on the dispersion of radio waves as they travel. This approach, often referred to as the FRB distance ladder, would add another tool to the astrophysicist's arsenal, providing a way to measure distances across cosmological scales with unprecedented accuracy. In turn, this could help refine our understanding of the universe's expansion rate, shedding light on dark energy and the ultimate fate of the cosmos. The expanding catalog of FRBs has also led to an increased interest in studying these signals in real time. Some observatories are now equipped with automated alert systems that notify astronomers as soon as an FRB is detected, enabling near-instantaneous follow-up observations. By capturing FRBs as they occur, scientists can coordinate observations across different wavelengths, optical, X-ray, and even gamma-ray, to get a more comprehensive view of the events associated with these bursts. This real-time approach may reveal transient phenomena, such as afterglows or emissions from other parts of the electromagnetic spectrum, which could provide further insight into the mechanisms behind FRBs. In the search for answers, one key area of focus is the repeating nature of some FRBs. Unlike one-off FRBs, which appear as isolated bursts, repeating FRBs emit multiple bursts from the same source, sometimes separated by hours, days, or even months. The existence of these repeaters suggests that different types of astrophysical events might be responsible for different types of FRBs. For instance, scientists theorize that repeating FRBs could be linked to highly magnetized neutron stars, or magnetars, which emit powerful flares that could generate these repeated bursts. The periodicity observed in some repeaters has led to the hypothesis that these objects may be orbiting another massive object, with the gravitational interaction triggering bursts at regular intervals. Some FRBs display exceptionally high levels of polarization, a property that indicates the orientation of the waves within the burst. High polarization levels suggest that the signals are passing through strong magnetic fields, hinting at environments with extreme conditions. This has led to theories that FRBs may be emanating from the immediate surroundings of black holes or magnetars, where magnetic fields are intense enough to impact the structure of the radio waves. By studying the polarization of FRBs, scientists hope to unlock more details about these extreme cosmic environments and understand the role that magnetic fields play in producing such powerful emissions. In parallel, there remains the tantalizing, albeit speculative, notion that FRBs could represent signals from extraterrestrial civilizations. The immense power, unusual regularity, and broad reach of some FRBs have led some to consider whether these signals might be artificial in origin, perhaps generated intentionally as interstellar beacons by advanced civilizations. Although natural explanations are far more likely, the prospect of an alien origin adds a layer of excitement to FRB research, reminding us of the vast unknowns that still exist in space. Even the slightest anomaly in FRB data, anything that doesn't fit expected astrophysical models, can reignite the possibility of intelligent life beyond Earth. Beyond potential alien signals, the study of FRBs also touches on fundamental questions about the very nature of the universe. For example, the existence of extremely bright, distant FRBs suggests that intense, energetic phenomena are more common in the cosmos than previously understood. The energy densities required to produce such bursts challenge current models of stellar evolution and explosion mechanisms, particularly since FRBs can outshine entire galaxies in radio frequencies, albeit for just milliseconds. Understanding how such massive amounts of energy can be released so rapidly has implications for high-energy astrophysics, potentially leading to revised theories about the life cycle of massive stars, neutron stars, and black holes. As the FRB research field continues to grow, it draws attention from a broad spectrum of scientific disciplines, from quantum mechanics to general relativity. FRBs provide a rare opportunity to observe extreme physical conditions that cannot be replicated on Earth, making them invaluable for testing theories in both quantum and relativistic physics. The intense energy, rapidity, and polarization of FRBs offer a natural laboratory for exploring interactions between electromagnetic fields, gravitational forces, and space-time, adding a new dimension to our understanding of cosmic phenomena. In the coming years, FRB research will likely benefit from new technological developments that could transform the field entirely. Innovations in data processing and signal detection will enable faster and more accurate identification of FRBs, while advancements in telescope sensitivity will allow scientists to detect fainter and more distant bursts. Additionally, international collaborations like the Square Kilometre Array will bring together resources from multiple countries, enabling a level of observational power that has never been available before. This collaborative approach is vital, as it allows scientists to pool their data and work together on solving one of the most challenging and exciting mysteries in modern astrophysics. The continued study of FRBs holds the potential to change our understanding of not only the cosmos but also the fundamental laws of physics. Each new discovery contributes to a larger picture, gradually unraveling the mystery of these enigmatic bursts and their place in the universe. As our detection methods improve and our catalog of FRBs grows, we may one day find answers to the questions that these bursts pose, revealing new and unexpected insights into the workings of the universe. For now, though, FRBs remain a profound mystery, offering us glimpses of the vast, unknown regions of space that still lie beyond our comprehension. Fast radio bursts remain a compelling frontier, not only because of their sheer enigma but due to their profound implications for astrophysics, cosmology, and even the philosophy of scientific discovery. These fleeting yet powerful signals push the boundaries of our understanding and challenge what we know about energy, distance, and the nature of the cosmos itself. Although countless mysteries abound in the universe, FRBs stand out as a particularly stubborn puzzle, resisting easy categorization or explanation. The combination of their staggering energy, pinpoint timing, and mysterious origins provides scientists with both an opportunity and a dilemma. While we gather more data, every new discovery seems to open fresh questions rather than offer concrete answers. In fact, the very difficulty in pinpointing a precise source for FRBs amplifies their allure. Some bursts appear as singular events, detected once and never observed again. Others, however, exhibit repetition, with signals coming from the same region repeatedly but often in irregular intervals. This distinction between one-off FRBs and repeating FRBs could imply that there are multiple types of progenitors, different cosmic events or objects capable of producing similar radio signatures under varying circumstances. For instance, repeating FRBs could arise from objects capable of continuous or cyclic emissions, such as highly magnetized neutron stars, magnetars, while non-repeating bursts might result from cataclysmic, one-time events, like the collapse of a massive star or a collision involving dense stellar remnants. The behavior of FRBs hints at another fascinating possibility. These signals may be generated within extreme environments, such as the vicinity of black holes or within highly magnetized regions. The polarization of certain FRBs suggests that they travel through intense magnetic fields before reaching Earth, implying that their origin lies in environments dominated by immense gravitational and magnetic forces. Such conditions are rare and difficult to study, as they are virtually impossible to replicate in laboratory settings on Earth. Yet, by analyzing the FRB signals, we gain an unprecedented glimpse into these extreme realms, helping scientists piece together information about environments where matter behaves in unfamiliar ways. In addition to offering insight into exotic cosmic locales, FRBs serve as a probe of the intergalactic medium, the sparse matter that exists between galaxies. When radio waves from FRBs pass through intergalactic space, they interact with this medium, experiencing slight delays as they encounter particles in the otherwise vast emptiness. By studying these delays, scientists can infer the density and composition of the medium, which has implications for mapping the universe's large-scale structure. This technique, sometimes called cosmic tomography, allows researchers to chart regions of the cosmos that were previously invisible, effectively using FRBs as a form of intergalactic radar. This ability to probe the intergalactic medium opens up new avenues for studying the distribution of dark matter, which is thought to be the scaffolding of the universe's structure. The mapping potential of FRBs holds particular promise for refining our understanding of the universe's expansion rate. Today, one of cosmology's biggest mysteries is the discrepancy between measurements of the Hubble constant, the rate at which the universe expands. Different methods yield slightly different values, leading scientists to question whether new physics may be at play. By using FRBs to measure distances across vast intergalactic stretches, scientists could potentially develop a new, independent, distance ladder to test and refine these expansion rate measurements. Such a breakthrough could clarify whether the discrepancies point to unknown physics, or if they are artifacts of observational limitations. Technological advances are rapidly transforming the way scientists detect and analyze FRBs. The current generation of radio telescopes, including the Canadian Hydrogen Intensity Mapping Experiment, CHIME, and Australia's Parkes Radio Telescope, have already accelerated the pace of FRB discovery. These facilities are optimized to capture signals across wide fields of view, dramatically increasing the number of FRBs detected. Soon, the Next Generation Square Kilometre Array, SKA, will dwarf existing telescopes in terms of sensitivity and coverage, allowing scientists to detect even fainter and more distant FRBs. The sheer scale of data expected from these new instruments will necessitate further advancements in data processing and machine learning to distinguish genuine FRB signals from the cosmic background noise. Machine learning, in particular, has emerged as a critical tool for FRB research. With the vast data generated by radio telescopes, manual analysis of every signal would be infeasible. Instead, algorithms trained on known FRB patterns can quickly identify potential bursts, filtering out interference, and refining the accuracy of detections. This capability is essential for identifying new types of FRBs or subtle features within signals that might hint at the physical processes generating them. Machine learning models can also help researchers identify statistical trends across large numbers of FRBs, potentially revealing hidden regularities or patterns that might otherwise go unnoticed. One especially intriguing development is the potential for real-time FRB detection and response. Some observatories now have automated systems that trigger follow-up observations within seconds of an FRB detection. This capability allows scientists to coordinate multi-wavelength observations, capturing information across the electromagnetic spectrum to build a fuller picture of each event. Real-time observations could reveal whether FRBs are associated with visible phenomena, such as X-ray or optical counterparts, which might indicate explosive or energetic events. Capturing FRBs in real time could eventually reveal afterglows or other transient signals that might accompany the bursts, helping scientists understand the life cycle of FRB sources. The periodic nature of some repeating FRBs has led to speculation that their sources may orbit other massive objects, such as black holes. If the FRB source orbits a black hole or another dense body, the gravitational influence could periodically trigger bursts, explaining the recurrence at predictable intervals. Alternatively, FRBs could result from interactions between objects within binary systems, such as neutron stars or magnetars, whose intense magnetic fields and gravitational energies create conditions ripe for powerful radio emissions. These recurring patterns, if confirmed, might even provide a new way of identifying and studying systems involving black holes or other exotic cosmic objects. Among the various models proposed to explain FRBs, the magnetar hypothesis remains one of the most compelling. Magnetars, a type of neutron star with incredibly strong magnetic fields, are known to produce powerful X-ray and gamma-ray flares. It's conceivable that certain magnetar flares could produce FRBs under specific conditions, especially if the star's magnetic field interacts with plasma in its vicinity to create shock waves. The magnetar model gained traction following the detection of an FRB-like signal from within our own galaxy, originating from a known magnetar. This event provided a rare local example of an FRB-like signal, adding weight to the idea that at least some FRBs may arise from similar highly magnetized objects in distant galaxies. Yet despite this promising evidence, the magnetar hypothesis does not fully explain all observed FRB characteristics. Some FRBs are far more powerful than any emission observed from a magnetar, and others display properties that are difficult to reconcile with this model. Additionally, while the periodicity observed in some repeating FRBs might suggest regular, cyclic phenomena, magnetar flares tend to be somewhat sporadic. Thus, while magnetars may account for some FRBs, they are unlikely to be the sole cause of this phenomenon. The diversity observed among FRBs hints at a more complex picture, possibly involving multiple progenitors. Some researchers have posited that FRBs could result from previously unknown astrophysical processes. These could involve interactions within dense stellar environments, high-energy particle collisions, or even exotic forms of matter. For instance, hypothetical objects such as quark stars, which consist of densely packed quarks rather than neutrons, might produce bursts under certain conditions. Another theory suggests that FRBs could arise from the collision of ultra-compact objects in binary systems, creating intense magnetic fields and shock waves capable of generating radio bursts. In the realm of more speculative ideas, some scientists have considered the possibility that FRBs might be signals from advanced extraterrestrial civilizations. The precision, power, and recurrence of certain FRBs have led to conjecture that they could be artificial, designed as interstellar beacons or communications. Though this explanation remains speculative and controversial, the very possibility captures the imagination and serves as a reminder of the potential diversity of intelligent life in the cosmos. While most researchers remain focused on natural explanations, the possibility of an artificial origin continues to be a fascinating, albeit unlikely, hypothesis. As we continue to explore and analyze FRBs, it's clear that they represent a unique and promising field of study with far-reaching implications. Whether they ultimately reveal new physics, unlock secrets of the intergalactic medium, or provide insight into the processes surrounding black holes and neutron stars, FRBs are certain to reshape our understanding of the universe in ways we can only begin to imagine. Each new discovery, each burst captured and analyzed, brings us one step closer to decoding this profound mystery. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.